So let's go into full screen. Okay, so welcome to the last part of PHY119, and we are talking about quantum communication. So whenever we talk about communication, we are talking about the secure transfer of information from one party to another. And whenever we need to do that, we use some sort of cryptography. And cryptography dates back to the ancient Romans or the ancient Chinese. So on screen here, what you're seeing is a device called the Caesar cipher, named after Caesar, who used this to encrypt some of the texts that he needed to send. So this is a pretty simple encryption device. It uses, So it basically uses a substitution encryption, which just means you are substituting one alphabet for another. For example, an example given here is that you would shift the alphabet a couple of places down the road. So an A becomes an X, a B becomes Y, and so on and so forth. So this is pretty easy to decrypt for modern computers, because if you're only sliding your text along, it means that there are only 25 different combinations to try before you can break the text. So obviously today in modern society, if you want to talk about the most secure cryptography scheme there exists, or what is the application that requires the highest level of security, this is probably the nuclear launch code for the President of the United States, whether you trust that person or not. So what happens is that daily, the National Security Agency would generate the code and deliver it in a suitcase in person, so either via a truck or a helicopter. So this is almost uncrackable, but for those of you who are interested in history, apparently, if you read this article here, it'll tell you that for about 1.5 decades, the nuclear launch code for the United States was 8 zeros. So not the most secure code you can use for something so important. So going back to classical cryptography, the only provably secure classical technique is the one-time pad. So this is when you have a truly random key between two shared parties. So conventionally, we have two communicating parties, and we call them Alice and Bob. So here, Alice and Bob would share a secret key of n bits. It needs to be as long as the plain text, and you would basically use the key to encrypt the text that you want to share. And you must do this only once. So it is the one-time pad for a reason. So provided the text is not used more than once, this can be proven to be unconditionally secure, and there is no technique that can crack the code. However, of course, there is one drawback. It needs to be as long as the plain text, which means this is very costly. And the cryptography schemes that we use every day does not use this technique. So all of this classical bits is just background. So modern day cryptography or most other schemes would use, so in order to avoid this having this very expensive key generation and exchange, we would obviously use a key that is shorter than a plain text. And most cryptography algorithms makes use of this assumption that certain problems are difficult. So they're difficult for modern computers to crack, modern classical computers. So the idea is to use a one-way function. And for a one-way function, if you have an input x, it is supposedly easy to compute the function f of x, but it is difficult to deduce the input x from the output, the f of x. So one example which is actually used is prime number factorization. So this is actually what the RSA cryptography system is based on. For example, if I give you two prime numbers, 67 and 71, it is relatively easy to compute their product given by equation 3 there. But if I give you the product, 4,757, it's slightly less easy to compute what the prime numbers are. So in this case, the user might leave a trapdoor open. So for example, the public key might be the end product, so the 4,000 number. So if I leave the door open for you, telling you that one of those prime numbers is 67, it might make it easy for you to compute the other. So that's how basic RSA cryptography works at the most basic level. However, such algorithms is not very easy to actually give a mathematical proof that they're actually secure. And for the particular problem of prime number factorization, mathematician Peter Shor showed that there exists a quantum algorithm that can actually crack this efficiently using quantum computer. So currently, the community is actually the mathematicians are working very hard to find post-quantum algorithms which are immune to this sort of quantum attack. And the quantum community is, of course, trying very hard to build a quantum computer. So classical cryptography might be breakable, which brings us to quantum cryptography. So in this course, we're going to look at basically 3 protocols. We're looking at the quantum distribution protocol BB84, which task there is to allow 2 parties to share a secret key, and it can be proven that this is unconditionally secure. So instead of assuming that the adversary has some bounded quantum computational power or bounded classical computational power, the protocol only assumes that the laws of physics hold, and they trust that quantum mechanics is correct. The second protocol we look at is superdense coding. So this is something that basically has no classical analog. So here we will show that if Alice is able to send 1 quantum bit to Bob, which is able to encode 2 bits of classical information. And then lastly, we will look at quantum teleportation. The lesson I want to take away from this is that you cannot do superluminal information transfer, so you cannot transfer information faster than the speed of light. But actually, everything is instantaneous. Well, the collapse of the wave function is. So, are there any questions so far? Okay. Cool. So this lecture will basically be some revision plus notations, and the next one will go into BB84. So as you would have learned from your first year quantum mechanics course, there are a few tasks which we can do quantum mechanically, which have no classical counterpart. So the first one cannot take a measurement without perturbing the quantum system. So if you have a quantum state and you perform a measurement on it, you will change the system. So here we talk about the collapse of the wave function and the Copenhagen interpretation, and so on and so forth. Secondly, one cannot simultaneously determine the position and momentum of a particle with arbitrary high accuracy. So this is basically the Heisenberg uncertainty principle. So number 3, one cannot simultaneously measure the polarization of a photon in the vertical horizontal basis and simultaneously in diagonal basis. So this is something that we will encounter later on, which is very important for quantum key distribution protocols, which is actually, it's basically where what the entire quantum cryptography, the field, what that is based on this. And one cannot, so number 4, one cannot duplicate an unknown quantum state. So this is also very important because, so this is basically saying that if I give you a quantum system and you have no prior knowledge on what it may be, so say for example, if I don't tell you that it's whether it's prepared in the horizontal, vertical, or diagonal basis, then you cannot duplicate that, and we'll give a proof actually later in this lecture. So quantum cryptography only assumes that the laws of physics hold, and the protocols, when implemented correctly, can be proven to be unconditionally secure. So if you're a mathematician who is slightly keener on the definitions, it means that if I have 2 communicating parties, Alice and Bob, and they share an n-bit key, so obviously the dimension of that system is 2 to the power of n. The last statement there means that the probability of an eavesdropper who is trying to hack into the system cannot guess their key correctly with probability higher than 1 over 2 to the n. So this is a negative exponential. And we know that negative exponentials are good for us in a cryptography sense. So this is good news. But we definitely won't go into the security proofs. If you are keen on reading some of those, you can ask me in an email. So let's do a bit of revision, and this should all be familiar to you. If not, please let me know. So when we talk about classical information, we talk about a classical bit. So this is either a 0 or 1. For quantum information, we talk about a quantum bit or a qubit. So usually the notation there is that we'll denote this to be psi in ket, and it can be in an arbitrary superposition of zeros and ones. So alpha 0 plus beta 1 is your conventional qubit. One condition that we need to set on it is that we require the amplitudes, probability amplitude to sum up to 1. So alpha squared plus beta squared is equal to 1. In vector notation, if we have a ket, this is typically a column vector. If we have a 0, then we'll denote this by this particular column vector over here, the 1, 0 in a column, and if we have 1, we denote this by a 0, 1. So for the particular qubit case, if we have a state alpha 0 plus beta 1, this is simply the column vector with alpha on top and beta on the bottom. So now if we have a bra vector, we take the Hermitian conjugate. So in vector notation, this means taking the transpose conjugate. So a column vector becomes a row vector. So once again, if we are transposing ket psi of 0 plus beta 1, now that we have bra psi, this becomes alpha conjugate bra 0 plus beta conjugate bra 1. And this will be a row vector containing alpha conjugate and beta conjugate. So I think you have met this during Peter Cox's course, first year quantum. Cool. So if we want to do anything to the state that's unitary, so for all intents and purposes in this call, we will only deal with unitary evolutions. So if we have a unitary evolution, it means that everything's reversible. So whatever I do to the state, if I know what I did to the state, I can undo it. So this is not exactly the case if we talk about classical computation. So I think the example there is like the XOR gate. So quantum mechanically, if we keep track of every step of the computation, you can always go back to the initial state and find out what the initial state was. Whereas in a quantum system, wait, sorry, I said quantum, right? Okay, so whereas in a classical system, if I put two things through an XOR gate, you don't necessarily know what the input is. So I think that may or may not be familiar to you. If you're interested, we can talk a little bit further about that. So the unitary evolution has to satisfy U dagger multiplied by U is equal to identity. Oops. Okay. So one very useful example of a unitary transformation is a beam splitter. So given by equation number 12 over there. So if you want to encode a qubit, basically all you need is a quantum system. A quantum system that has two levels. So the two encodings may be path or polarization. So I'll show you a quick example of what these can look like. So if we, oops, not that one first. Nope. There. So if we talk about path encoded qubits, a beam splitter, can I make this bigger? Yes. What a beam, okay, so if you talk about path qubits, so for example, I may have a flying photon that comes in from the left to the right, and what a beam splitter does would be it will put the qubit in a superposition of going straight or being reflected. So this is a beam splitter cube that you can buy from Thor Labs, pretty standard optical component. You may have seen this in first year labs. So obviously this thing has a dimension of, in the order of a centimeter. You can equally put this on an optical chip. So so apparently I was told that this is a course that is supposed to stimulate your research interest. So I'll show you some real life examples of how this actually comes into my everyday research. So this is a chip, an optical chip that's fabricated by, that's currently at the University of Bristol. I think they get somebody else to make it. So this whole thing that you're looking at here can be as small as millimeters. So these structures that you see here can be in the order of I think 50 nanometers. That's the dimension they're quoting. So I think this is a silicon chip, and these gold things here are electrodes. And we won't talk about what they actually do.
It turns out the screen's black, so we can't actually see the photo.
Oh, sorry.
Yeah, don't worry about it.
What are you? Okay, you're actually seeing a black screen.
Yeah, we can see the PowerPoint, but then when you switch to the whatever it is on now, we can't see it.
Okay. Is it still black?
Yeah, it is.
Okay. Let me try this for. Okay, stop sharing. And then I'll go a window. Okay, good. Okay, what are you seeing right now?
Oh, we can see it now. Yeah, we can see it.
Okay, so right now you're seeing the beam splitter cube, I presume. It's a cube thing with a black stand that's holding it. Okay, so this is the beam splitter cube that I was talking about. So can you actually see my mouse, by the way?
Yeah, we can see your mouse.
Okay, good. Yeah, so there may be a photon that is coming in from one of the sides, and it may choose to go straight or get reflected. Actually, in this case, it'll be coming in from the back. So the photon will either go this way or this way, and we say that the photon is in a superposition of heading straight or being directed. And now, let's see if I can show you the second photo. A window. Okay, good. So if you can actually see the chip, this is the chip that I was talking about. So this entire structure, the thing in red there, is in the order of millimeters. So the previous beam splitter cube, that's about 1 centimeter, is one of these Mach Zehnder, well, okay, couplers that you're seeing. So if I zoom in onto one of these, it'll actually look like, okay. Now I'm going to show you a window. Okay. So yeah, so that previous beam splitter there can be condensed down to this thing over here, oops, which is called a directional coupler. So what happens here, that if you inject light into one of these waveguides, if you get the coupling distance between these two waveguides correctly, turns out you can make the light come out 50-50 on this path and this path. And we call that dual rail encoding. Okay, enough of that. Let's go back. Okay, and I hope that my presentation's come back, which I think it has. Let me know if it hasn't. Okay. Full screen. So let's continue with the revision. So if we have two states, X and Y, we can calculate their state overlap. This is the quantum overlap. So we put them together in a bracket, X overlapped with Y, which is equal to the conjugate of Y overlap with X. And the probability of measuring X given the state Y would be given by their overlap squared, well, the absolute value of the overlap squared. So that's given by equation 14 over there. So basically, all you need to know for this course is that 0 overlaps with 0 to give you 1. That's the overlap, and 1 overlaps with 1 to give you 1. And obviously, 0 is orthogonal to the 1, and their overlap would be 0. doing a really easy example. So if we define a plus state, which we'll use again later, to be an equal superposition of 0 and 1, so this is 1 over square root 2, 0 plus 1. If we are calculating the overlap of the plus with a 0 state, so to do this, you would overlap the broad 0 with the ket plus. And now you just, so everything's linear and associative, so just bring out the 0 with a 0 and the 0 with a 1. So 0 overlaps with 0 to give you 0, and the 0 overlaps with the 1 to give you 1. So at the end of the day, you end up with 1 over square root 2. And this is, remember, this is a quantum overlap. Now, if we want to calculate, so what this means is that physically, is that if I have a plus state and I want to measure it in the basis broad 0, then this is a quantum overlap, but the probability of the measurement outcome would be the absolute squared of that, and of course this case is just 2. Oh, sorry, 1 over 2. So I think you should have done that also. Okay, and now we get to one of the results that you haven't seen before. So this is a version of the proof for the statement that it is not possible to make a copy of an unknown quantum state. So this is one of those proof by contradiction statements. So let's suppose that there is a procedure prescribed by a unitary process U that can copy the states 0 and 1. So the notation there in equation 18 is that we need to bring in an auxiliary system S, because so if you want to make a copy, okay, so somebody else has joined for the last 30 minutes, which is fine. So the notation there is that the 0 state in equation 18 is the original system that I want to copy, and I want to copy it onto the state S. And suppose that the procedure can succeed, so I end up with 2 copies of the 0 state. Is that clear to everybody? Okay. And now, because I'm claiming that the unitary can copy 1, then I bring in the state 1, and I bring in my auxiliary state again, S. Then then after the procedure, I will end up with 2 copies of 1. Now, suppose that the state we want to copy is now an arbitrary state psi alpha 0 plus beta 1. So what we do is that now we bring in our auxiliary system S, we put it together with the state that we want to copy, psi, and we put the same unitary in front of it. So because quantum mechanics is linear, so the unitary acting on alpha 0 and S would give you alpha 0 and 0. Now the unitary acting on beta 1 together with the S state will give you 2 1s. Now, if we look at the state in equation 19, we have alpha 0 0 plus beta 1 1. And note that this is strictly not equal to 2 copies of the state psi. So what does this actually mean? It means that we can't actually make a copy of an unknown quantum state. So there's a slightly more rigorous version that's in the notes I've uploaded if you want to read it. Yeah, basically we arrive at the conclusion that it is not possible to perfectly clone an unknown quantum state using an unitary evolution. And the caveat there is unitary evolution. So there are some things which you may be able to do, but it is not deterministic, which means you can't copy an unknown quantum state deterministically, i.e. with probability 1. And so this is actually great news for quantum cryptography. And I think I'll go into that in the next lecture. So are there any questions so far at this point? Is everyone happy? Not happy? Is this intuitive? Is it, okay, so is it actually clear to everybody that alpha 00, does anyone want me to do another board that alpha 00 plus, oh, there's supposed to be a beta there, plus beta 11 is not equal to 2 copies of psi? Okay, well, let me do it anyway. Okay. Sorry, I'm just getting my well, virtual blackboard. Okay. Okay. Oops. Okay, so is everybody actually still seeing my presentation? So what I want to do, window, I'm gonna share that. Okay, good. So if U is actually, wait, where's my pen? There's my pen. Okay, let me unplug. Okay. I am presenting. So is everyone seeing my blackboard okay? My, well, whiteboard. If not, give me a shout. So, so originally I have psi is equal to alpha 0 plus beta 1, right? So if I successfully copied the state, I have psi supposedly equal to alpha 0 plus beta 1 tensored with alpha. I'll go into 0. I'll go into the tensor product later in the lectures, so probably next or one after 1. So this is equal to alpha squared 0, 0 plus, well, okay, so actually for tensor product, you actually just multiply the vector, the components together respectively, so you end up with alpha beta 0, oops, 1 plus beta 1, 0 plus, oops, beta squared 1, 1. So, Oops, okay. There. So if my procedure is actually able to copy the state, this is what I should end up with. It's this whole thing over here, and this is obviously not equal to alpha 0, 0 plus beta 1, 1. So, oops. So we have our, well, toy proof. Cool. Now, so present now a window. Show this. Okay, so that was all I was going to do for today. So does anyone have any questions? We have a lot of time. Anyone want to hear more stories from quantum mechanics? Anyone wants anything debunked? I'm all yours until, well, 3 o'clock. Okay. These are recorded indeed. I will put the link to the recording online, maybe on YouTube. But if you think I went too slow, too fast, probably too fast, and you want me to go over anything again now, I can do that too. So everybody's happy for now. So yeah, so basically, you've probably heard from the announcement that this lecture course is not assessed. So I presume that you're actually here because you're interested in the material. So I'm here for your own learning benefit, and you've also paid for it. So feel free to ask me any questions. Otherwise, I might see you on Thursday at 5 o'clock. And we will start off with, let's see what's there. Yep, so next lecture, to give you a mini trailer, we'll start off with measurements in quantum mechanics. So what happens when you actually collapse a quantum state, what you end up with. And then we go into our first quantum communication protocol, BB84. Cool, awesome. So if nobody has questions for now, I will see you next week.
Thanks.
Oh, awesome.